It's Miss Turley, and we're finishing up our notes from buffers today. So we left off with looking at this Ka expression for a generic weak acid dissociating into H plus and X minus, its conjugate base. And we said that if we wanted to find the pH of the buffer solution, we can write out our Ka expression and actually rearrange for H plus and see that our H plus concentration and therefore our pH is related to that Ka value for the weak acid times the acid concentration divided by the base concentration. So the pH of your buffered solution is dependent on both the Ka for that acid that you've decided to use in your buffer, as well as that ratio between the acid and the so now we're going to look at how to select a particular type of buffer. So because buffer systems can have different pH values, and in industry you may need a pH of a of a specific value, like a pH of 3 for a specific chemical reaction to happen or for your blood you want it to be at a specific pH. It's helpful to be able to figure out how can we not only calculate the pH, but how can we select appropriate acids and bases to get at that good pH region. And we're going to see that if we choose different conjugate pairs, we're going to end up with different pHs for our buffer system, and that this is really dependent on that Ka value. So from the last equation we saw that if the HA, the acid concentration, is approximately equal to our base concentration, then that would be 1, no matter what their concentrations are. If they're the same, if they're both 1 molar, if they're both half a molar, they would cancel out to just be 1, so that our H plus concentration is equal to our Ka. If we took the negative log of both of those sides, then we would say that our pH is then equal to our pKa. Remember, pKa is just the negative log of the Ka value. So therefore, we see that if we know the Ka values of different acids, or the pKa values, that's going to tell us what pH that buffer system is going to make if we use the same amount of both the acid and the base and the same molarity for them. So for example, if we wanted to make a buffer with a pH of 4, let's look at this chart of all these different weak acids. There's a ton of them, and this lists the acid name, what the actual acid formula is, what the conjugate base is, and the Ka value, and then the pKa value. Once again, that pKa is just the negative log of that value. So if we want a buffer with a pH of 4, we want to look in here. We got some pKa values close to 4. The lactic acid is a little bit less than 4. The ascorbic acid is a little bit greater than 4. So we would want to start with one of those two acids along with its appropriate conjugate base, and we could actually even calculate how to adjust their concentrations accordingly to get a pH of exactly 4. But for now, we want to realize that at least these two acids would get us in that ballpark. For example, if we used chlorous acid up here in its conjugate base, if we had equal concentrations of both that acid and base, our pH of our buffer would be 1.96. That's pretty far away from 4, so at least this can get us in the right ballpark range. And if we think back to this equation back here, we could adjust that ratio, maybe make it not 1 to 1 to make that pH exactly equal. So the buffer capacity is how much of an acid or base the buffer can actually neutralize before the pH really does start to change. And this is what we looked at the simulation a little bit for. There's only a certain molarity of your acid and base, your weak acid and your conjugate base within the buffer system. And if you neutralize it all out, well, then you're just going to be adding straight up H plus ions or hydroxide ions, which is definitely going to start to change your pH significantly. So for example, if we have a 1 liter solution that's 1 molar in acetic acid and 1 molar in sodium acetate, and we also have a different buffer system that's only 0.1 molar in acetic acid and 0.1 molar in sodium acetate, even though like they're the same buffer system in terms of what acid and what conjugate base is present, and therefore they have the same Ka value and they would have the same pH. The first solution that has these greater molarities has a greater buffering capacity because there's just more moles of that weak acid and that weak conjugate base present, so it would be able to neutralize more strong acid or strong base that's added to it. So the greater the concentrations of the conjugate acid-base pair, the more resistant it's going to be to actually get that pH to change when adding a strong acid or a strong base. So now let's look at a practice problem. You may be asked to calculate the pH of a buffer system, and here our buffer system is not exactly the same molarity, right? We have 0.12 molar of the actual acid part, this is lactic acid, and we only have 0.1 molar of sodium lactate. So our first step is to kind of write out our equation and write out an icebox. If you want, you can pause the video and just go ahead and try out this problem all on your own, see if you can do this, and then resume and kind of watch me walk through the steps. So here we've got our actual equilibrium expression of the lactic acid, and it's dissociating into the H+ ion and then this lactate ion, the A- or that base, the conjugate base. And we knew that we are starting with 0.12 molar of the acid and 0.1 molar of, in this case, it was sodium lactate. Well, we don't really care about the sodium, right? The sodium is just a way to supply this lactate ion into the buffer system. So this, we're going to kind of assume that our equilibrium system is saying that we are, you know, a little bit of this is dissociating and forming a little bit of our products. Really, because we don't have any of our H+ ions present, that's the only direction our equilibrium can go, right? We can't go in the reverse because we wouldn't have any of this to use up. So since we're starting with 0 H+, our equilibrium is going to shift to the right slightly. We can put in our -x or +x's, and we end up with x for equilibrium of H+, and we're going to, these are crossed out in yellow because we're going to assume that that change is negligible, and it really is going to be negligible when we look at what x is. So go ahead and set that up with your Ka expression, and let's solve for x. Once again, if you want to just pause it right now, with this step in mind, see if you can do the next on your own. So here we go. Here's our Ka expression, our products over our reactants. I set that equal to the actual Ka value and plugged in our E row from our table. And then we need to solve for x. So if we solve for x, we get 1.6 times 10 to the -4th molar, and that is our H+ concentration because that's what x was equal to in our ice table. So then we can take the negative log of our H+ concentration to get a pH of 3.77. So that's the answer to our question. So it's really not very different from the ice tables that we've been doing before. It's just that really now it's a common ion example, similar to solubility, where we were starting with this initial concentration of both our reactant and one of the products. And we get a pH of 3.77. So now what we're going to look at is an idea that because we always have this same relationship where our H+ ions for buffers is equal to our Ka and then our acid over our base, we end up seeing that this process is pretty repetitive and we see the same things over and over again. So we can actually derive an equation for buffers using these assumptions. So if we account for the assumptions, you know, that we can always assume that x is small for buffers, then the following equation can be derived. And this equation, it's written a little bit differently on your useful info sheet, and I'll show you the exact version that's on your useful info sheet in a second. But this equation is called the Henderson-Hasselbalch equation, and it's really helpful to use for buffers. And I'm going to quickly go through the derivation. You would never need to be able to go through the derivation, but it's good to know that this is a shortcut of how to do buffer problems where you don't actually have to do the whole icebox method out. So if we think back to the fact that our Ka expression for this reaction is H+ times A- over Ha, and once again, this comes back from just our overall dissociation of any generic weak acid. We can rearrange it into here, and this is that same rearranged equation we talked about just at the beginning of this screencast, where our H plus concentration is equal to our Ka times our acid over our base. We can take the negative log of both of these sides of the equation, because that's going to end up giving us pH, because the negative log of H plus is pH. So if we take the negative log of both sides, we're getting the negative log of H plus, which is equal to pH. And then we have the negative log of this whole thing, Ka times this Ha over A minus, which is really our acid over our base. We can break this up using log rules, and I'm not going to explain why these log rules exist, but I think you learned them in math, and if not, I don't really want you to worry about it. Just trust that this math is sound. Because this is being multiplied within a log function, if we want to break it out and take the log of both of those, that's an addition. So the negative log of Ka plus the negative log of this ratio of acid over base is what this kind of expands out to. And we know that the negative log of Ka is what the pKa is. That's what that's defined as. Just like the negative log of H plus is pH, the negative log of OH minus is POH, the negative log of a Ka is pKa. And then for this last piece, since we now have a minus log of acid over base, technically we can flip the sign, and if we flip the sign of it to turn it to positive, we just flip the ratio in here of which one is divided by which. So this equation is actually exactly what appears on your useful info sheet. The pH of a buffer is equal to the pKa of the acid used plus the log of the concentration of the conjugate base divided by the concentration of the conjugate acid. It's very similar to this one that's written on your note slide, except on the note slide just wrote base over acid. On your useful info sheet, that shows up as A minus over HA. So we can do this lactic acid problem that we just did out kind of our long way with our ice table using this equation. So go ahead and try doing that, and you should still get it, oops, sorry about that, still should get a pH of 3.77. I'm not going to walk through that right now, but we can check in at the beginning of class to make sure using this equation is smooth, and we'll look at some more examples. All right, have a good night.